Okay. All right. So actually, Dima proposed as the main topic of this conference the following equation. You take Lie theory. You subtract. Yeah, you subtract groups. And then that's a question mark. Actually, I learned so many things from Dima. One thing I learned is that the key to solving any problem is to remove. How would you translate лишнее? Yeah, unnecessary things. So you should do. You take Lie theory. You remove the unnecessary. So лишнее. And this contains groups. And then you should be in better shape. And then what would you like to see on this side? Well, you'd like to see something remain, right? And then obviously, what's the highlight? What's the main result in Lie theory? Well, I guess everybody in this room that think that this is cardinalistic theory, so that certainly has to contain cardinalistic theory. No. This will be, as opposed to some other talks, this will be a theory talk. So it has some knowledge in it. Yeah. So I'll tell you explicitly when it's not, when I left my feet off the ground. So, and then of course in cardinalistic theory, there's one ingredient we all know and love. I mean, this is somehow the basic ingredient, and it's the Hecke algebra. You can of course discuss. You can algebra. And okay, so this is you can discuss categorical version, but let's think of just algebras and operators. And so, what is Hecke algebra? Oh yeah. Yeah, that's right. So, what's Hecke algebra? Well, if you look at the poster of the conference, there's of course a beautiful street of Jerusalem. It's also an affine hyperplane arrangement, something like this. So, and everything's going to be in this talk will be affine, and so so Hecke algebra is, well, you start with affine. So there you take affine Weil group. Will be affine Hecke algebra affine Weil group. Then you go, well, you replace it by really some kind of braid group. And then you map it here. Right? You impose, so Hecke algebra is a braid group of something like this. When you impose the relation, what are the monodromy around each one of these hyperplanes? And well, now we look at this, and we see an unwanted word appear on the side. We don't want the group word on this side of the equation. So this is bad, as Denis would say. Right? So we don't want this. And how will this manifest itself?
Actually, it appears twice.
Yeah, right. Yeah, exactly. Yeah. So, but that braid group is somehow okay. So yeah, Pasha. So how will it manifest in the side of this picture? Is that the arrangement with which we'll have to deal, they will no longer be homogeneous. There will be no. So the Weil group arrangement, they're extremely nice in that there is a group of symmetry that makes all alcoves look the same. And this is a very basic thing I learned from Roma a long time ago. I guess I could have also learned from Dima. This particular one I learned from Roma. So this is that in general the arrangements will see that they will be still of the form. There's some coordinate x, and you have some set of roots. So alpha x is an integer. But alphas now, for example, they could be proportional alphas, some set of alphas. So if you write some set of alphas, you're going to see an arrangement. This is a little bit like Ivan Stock. Ivan wanted to keep it to the roots of Kac-Moody Lie algebra, but in principle, you can have an arrangement like that. And then, of course, the right notion is not the right notion is not. We don't want a group of symmetry of this. We'd rather want just the. So I'll erase this. What we want really is we'd like the fundamental groupoid of an arrangement like that, and then imposing what are the monodromies around each one of these walls.
Groupoid is fine.
What?
Groupoid
is fine. Yeah. So then this will get us what the Hecke algebra will be. But in fact, we will look at something even more general. So this is. In this more general, we'll specialize. So this is exactly the kind of thing that appeared in Roma's lecture, will reappear again. So in that situation, this Okounkov parameterize various T structures on a certain category, and the equivalences form that groupoid I'm talking about. But in fact, it'll be even more general in that this is you should really think of this as a picture of this happening. This is a picture in the Lie algebra of some torus. So really you should think of this as not an arrangement of hyperplanes in the vector space, but rather an arrangement of subtori inside the torus. And associated to every so there's a maybe I should have drawn this picture bigger. But okay, well I did what I did. So there's a wall to every wall of this arrangement. We call it W. You'd like to associate an operator, which is rational, so to a wall W. We associate an operator that depends on the equation of that wall. So meaning if my equation is alpha dot x plus n equals 0, this if I in the exponential coordinates means I'm going to be looking at something which depends on say q to the n x to the alpha. Where q is a q. We'll get to what the q is, but for now you can think of q as just some number in the multi. It's not the parameter of a quantum group.
My
Yeah.
question is the integration of your wall gives another wall,
Yes.
but it gives the same operator.
No.
But A you are alpha and N are C.
But the operator depends on the wall. So the kind of right. Yeah. So this is the familiar in familiar staging. If you try to define a root operator in the quantum group, something corresponding to a root subalgebra that corresponds to a choice of factorization of the longest element, and this corresponds to an order in which I'm going to cross all walls. Right, and this will satisfy. So this will satisfy the braid relation, meaning if I go, if around the vertex I go this way or that way.
Wait, what are you doing? You're defining an algebra right now.
Defining, I'm writing an equational set of operators, meaning if I the operator in some vector space. This act on something vector space. And they satisfy a relation that if I go around this, well, again, I do the same this. So example of this is a Young-Baxter equation. If you think of a Young-Baxter equation, it's an equality of three operators. And each depend, Young-Baxter with a spectral parameter, each depend on three variables through the equation of the wall that we're crossing. And then there is from this. So this is a relation I want. And then from this, if we send this variable, if we take these variables and send them to 0 or infinity, we get two different operators that correspond to crossing. You can interpret them as crossing this wall. So if you have a, say if I have a, no, that's the argument. It's a function of one variable. So that variable you can send to 0 and infinity, and that means that this is my parameter space. There is a wall here, which is my wall W, and in the complex plane I can cross it over, or I can cross it under, and this will be correspond to these two different limits. And if I take a limit like this, then from a representation, I would call something like a dynamical groupoid. An example of this is the usual dynamical. So Pasha and Tvarchenko studied the dynamical affine Weyl group for quantum group. It's an example. And this, from there you can take this limit and you get representation. So now in this limit you find the representation of actual fundamental groupoid. This will satisfy the relation. The relation in fundamental groupoid are the relations that 3 over crossing like this equals 3 over crossing like that. Is everybody with me? Yeah. Oh, you require, no, this relation you require always. It's like Young-Baxter. Means if I take, so maybe I'll write this down. Since this is, you have 3, you have 6. I mean, I wrote an example, could be more. So I wrote an example with 3, 4, 5, 6. So you'd like an equation that the product, if I go, in other words, maybe I'll write it like this. If I go around, this product of B and W i's equals 1. Because this is a representation of, this is also a representation of some different relations. If you'd like a representation of fundamental groupoid, in the fundamental groupoid you have an overcrossing and undercrossing, and this corresponds to taking this value to infinity to plus. Yeah. Other questions? And then we would like, and this is the kind of structure we want. Then the description. So maybe the bulk of lecture today, I'd like to explain. What would I like to explain? What the main examples of this sort of things. And then the description of like a Hecke algebra description would be saying that I'd like to specify the conjugacy class of going over. I mean, I'd like to specify the conjugacy class of these operators. But in fact, I can specify the conjugacy class of going to the opposite, like in Ivan's lecture. In Ivan's lecture, there was a special notion is if you have some chamber and you cross to the opposite with respect to a certain phase. So geometrically, this will be the most significant ones. And the simplest example is just crossing one single wall. No, so the equation is that this product of the corresponding, so to speak, x to the wall equals 1. This relation. Right? And one more thing is that this is
X is no X. What is it? Is it the same X or
man, I don't know. I mean, you want the variable. This is the variable in the group, and this is the variable in Lie algebra.
Yeah, but the number of parameters is the same.
Same, yeah. This is the Lie torus of a group. And instead of integers, you have one. Yeah, sure. So, okay. That clear? So, something else I wanted to say is that there is a certain, you cannot, whatever you consider, there'll be some group of symmetry. So you cannot, maybe a trivial group. But whatever you consider alive, it has a certain group of symmetries. So you cannot really get away from the group. Right? And so in this situation, there is some residual group of symmetry. For example, there is a lattice translation. And then what would you like to do, what you'd like to require, is the arrangement. If I write it like this, it's there's some translations by a lattice. So if alpha lambda is an integer, then translating by a lattice element like this is a symmetry of this arrangement. And what would you like to have is that the operator that corresponds to wall translated by lambda. This of course will depend on its own whatever the equation is. So this will be like q to the corresponding thing. This is where lambda will enter here. So this will be there's some part which is pair of this alpha lambda plus whatever n it was times x to the alpha. Then so you would like this operator will not be exactly equal to the operator BW, but maybe it'll be conjugate by some other operator which forms a representation of my group. So. If that is the case, so this is the case we will always consider. If that's the case, you can write commuting difference operator from this data. Namely, if you take so the way you write is that if you take the translation, write translation by minus lambda, then O minus lambda, and then you take a product of this B wall along any path that joins your base point. You have some based alcove. You go to this alcove plus lambda. Choose a path and you multiply this operator. This operator's commute. So this will be geometrically significant operators for us. This translates variable x. So this t lambda sends x to alpha, sends to q to the, so this is what t lambda does. T is q to the alpha lambda. There's a q difference. This will be a family of commuting q difference operators. So this would be this quantum difference operators. And the shift operators. So just find geometrically what these guys are. Maybe I'll say it now. So this is maybe it'll be easier once we put ourselves in some context. What is this torus? Pasha, wake up. I mean, this is. I need you to interact with the talk.
Yeah,
You listen.
I'm sure.
So the torus we want, there'll be two geometric incarnations of this torus. There'll be some variety x, which, so I'll get to the exact nature of x later. X is kind of like simplex resolution. It's not exactly simplex resolution. I mean, there's some class of varieties I'd like to consider is not equal to simplex resolution. So, but there's some variety x, and so the torus could be either pick x tensor multiplicative group, and if I'm forgiven, can I write the node multiplicative group C star? I think it's somehow it's okay. Yeah, exactly. C star. It's one version. This is one incarnation in which we'll discuss what are these roots, what are the roots alpha, and the operators you get from this will be this quantum difference operator that generalize the connection that Davesh discussed. It's a difference connection. And also in this limit here, you get the monodromy that Roma was discussing. So you have some. So in this limit, so Roma's arrangement lives literally here, I mean in the Lie algebra of this group, and it's going. All these derived equivalents define you a representation of a fundamental groupoid of this arrangement, and that is this limit from this quantum difference equations.
So whatever class of rights you consider, the car will always be limit.
Yeah, right. Yeah. So this is one version, or it could be just, so maybe we'll denote it, so maybe this torus in the future will denote it Z, and the variables in it we'll call little z, or it's just the maximal torus A, or some torus for that thread, but might as well take a maximal torus in symplectic automorphisms of X. In which case these operators will be the shift operators that diverge this kind. Well, I guess slightly ran out of time discussing, but we will try to make up this. And then in this case, it's easy to say what the roots are in this case. The roots are just so this picture here. What is this arrangement? This arrangement is just literally R. The arrangement I'm talking about here is just literally trying to. So this is the locus of A in the Lie algebra of A, such that the fixed locus of A is not equal to the fixed locus of the whole torus. Right? In other words, this alphas. What? No, because it can have a finite group. In particular, the group generated. So this is the group generated by this guy. Need not be connected, and you treat fixed loci of finite groups just as well.
So XA by definition is X of XA.
Of XA, yes. Yes, I apologize. So it's really an arrangement on. I keep writing. I really write an arrangement of subtori in a torus, and right. Thanks you. And these alphas, the set alphas, these are just these roots, so to speak, equivalent roots. These are the weights of alpha in the normal bundle to the fixed locus. And what is it for T star G mod B? If we'll take the maximal torus acting on maximal torus of G acting on G mod B, the weights in a tangent space at any point, let's say at identity, are by definition the positive or however defined, positive or negative roots of your Lie algebra. So this is quite literally generalizes this notion. And so this is maybe a parallel statement here is that where do we also see this arrangement? If we look at equivariant K-theory of X or equivariant elliptic homology of X, that is the spectrum of that is some scheme that lives over. Oh, Mike woke up. It's a scheme that lives over either the torus itself or the torus or the co-character lattice cross elliptic curve, because the base elliptic curve, and that scheme there's some specification of that scheme. It changes precisely over this loci. So, like for example, the fiber of equivariant K theory over a point is really the K theory of this fixed locus. So, one more general notion before I go to maybe more specific examples is that if I have this, maybe I'll look at my notes and make sure I've. I said what I wanted. So if I have, so maybe we'll close this for a second. So if I have so if I have this commuting, these are commuting difference operators, and one can study solutions of the corresponding Q-difference equations. So formally, this is something very, very easy. So if I have an arrangement and I picked an Okounkov, then if I just take a path to infinity and multiply all wall matrices from here to some infinity, then this is formally solves that Q-difference equation. Or rather, to say that this product, this infinite product of all matrices, this is better to say it's regularized by the solution of its proper regularization is solution of a Q-difference equation with specific asymptotic. So because here going to infinity in the Lie algebra means going to infinity in a certain. So there's this roots alpha define for me a toric compactification of my torus. So there's my torus here. Well, let's say for concreteness we'll call it Z. And then, so this will have a certain compactification, Z bar. What is that compactification? The compactification corresponds to the fan of the chamber of the fan formed by this by my roots. And what it is for my Kähler? Is that everybody's somehow comfortable? I'm just saying this. This means so I choose a path to infinity. It now crosses all hyperplanes sufficiently here. Which means it has to. Right. That means I have to look at linear parts of my roots. So if I just if I take associated linear arrangement. So let's just put the central arrangement, take all of my roots and put them through the origin. Means I have to choose a chamber of this arrangement. And so this says how I'm going to cross all hyperplanes. Okay? Which corresponds in the terms of, if I look at the torus, then this fan formed by my roots gives me a torus compactification.
But it's affine.
No, I take a toric variety that compactifies my.
Could also variety correspond to all possible directions?
Exactly, yeah.
It's one direction. So this is what I was.
That's right. Right. And so this is you get. So in other words, the choice of infinity where to go, it's a choice of a fixed point in the toric compactification. Here. And what is this? What is this in terms of, so if Z is my, so if Z is px all times C star, that this is a choice of an ample cone. These are the ample cones of all birational models of X. And this toric variety, it's what's called the Kähler moduli space. It's a toric again. It's a variety in which this points parameterize various birational models of your variety. And the solution of this equation near this point, so this is the solution. So this would be this infinite product. This form means the way to regularize it is to write a solution of the Q-difference equation at this point. That solution is this. So it means here I choose a specific birational model. this is somehow, this relates to Denise's question some number of lectures ago, is that you write quantum connection as a connection, so or quantum difference equation as a connection over the historic variety, but you kind of geometrically it comes expanded in various directions, and this means the direction in which you expand are parameterized precisely by all possible slopes of your variety x. And so then this means this is specific variation mode. This will be this I don't know, what do you call it, the whatever J function or some such thing. So these are the equation itself, and its solution has a certain meaning in terms of curve counting in that birational model. So this is somehow there's some image of information. To which we will get. But right now I'd like to say one thing which is maybe to set one of the directions in which we're going to go, is that you can ask, how do I compare this solution corresponding to different infinities? In this picture, if I'd like to say, like if I choose a path here, then if this is a solution of my codifference equation, then an infinite product like so, well, it does have to go to the opposite infinity and go to some other infinity. This infinite, so an infinite product is a ratio of two solutions. So it's really, so maybe it goes to some, let it go to some slightly different infinity. And so this means comparing this infinite product is the comparison between a solution here and a solution at some other. This is, so you kind of, so a solution of Q difference equation, they don't have, the monodromy of a Q difference equation is a better thing than the monodromy of a differential equation, in that it's not a representation of pi1, just one matrix. You write the solution near one point. By the Q difference equation, it meromorphically extends to the whole thing. And so then if you take the solution at another point, it will meromorphically extend. Take the ratio of them, this will be an elliptic function. Which is formally, it's clear, if you take a path going to infinity in both directions, therefore obviously it's by the fact that by relations, it doesn't matter where the path goes, so that's going to be obviously translation invariant. So this would be an elliptic function. So you get, so this thing is some elliptic function that corresponds to x and some slope of x. This will be. I hope I'll get to that point, because this is a very important. I think this is a very important ingredient, this elliptic function. What I think it is so is that the setting of the, I don't know. I'm trying to mix some very elementary things about elementary algebra with some things I haven't explained, which is, but what?
What will the elliptic function be upon?
So it's an operator on the same vector space on which this guy acted. So all these operators were acting on some vector space, which you think of this should be, this vector space should be a covariant K-theory of your variety X. Right, and so then you get an elliptic. Yeah, sure.
Do you really have some functors in the category calculation?
Right. So this, yeah. So let me say one thing, and then you can ask your question again. So what I think, and this is something we've been doing with. So this has been something we've been doing for a while, but without a progress to report. But what I think this thing is that this is. So this is really a map. This elliptic function is really a map from some shifts on elliptic the current elliptic homology of X to elliptic homology of a flop. So this is this is like in Roma's situation. In Roma's situation, you had different. Well, I mean, you can compare and contrast what happened in Roma's talk. Well, it will happen again. So this is in his situation. You had the derived equivalence between X and a flop of X. There were many such, and even the reaction on K theory was somehow even their reaction on, they even acted differently on K theory. So there's this monodromy we're discussing here. This monodromy. This is really just this. You can say that this comes from different. So the monodromy will act on this space. What is that action? Is if you identify X and its flop in derived sense in many different ways, and a corresponding action on K theory are all different and generate that fundamental group Y. Right. Yeah. Yeah.
So you have X and X flop.
Mm-hmm.
Do you expect that category of shifts are actually equivalent?
So what I expect is that this guy comes. So there's a map from here. This is like the K theory of some category of certain. I'm not going to describe it. Some kind of shifts on loop X. Yes. This. So if I have a shift on a loop group, then this maps here, and this. I'm not going to just describe now what kind of shifts I take. These are coherent shifts. Coherent shifts of certain kinds on maybe universal cover of loop X. Same for the flop. And we'll certainly expect a map. So we certainly expect this an equivalence here. Now this will not be this equivalence as opposed to this equivalence is just one equivalence. There's not a multitude of these equivalences, and so therefore it corresponds to just the monodromy being just one matrix.
Let me ask the same question.
Yeah. Uh-huh.
You asked me talking about global.
Mm-hmm.
I think about going around the
Yeah, exactly. And so you would think that maybe there's some variation of stability condition that gets you from loops of X to loops on the flop in countably many steps. That's what I know. You'd imagine there's something like this. So there's some anytime, since this talk is going to be about curve counting, and anytime you see some operators, what? Okay. It's difficult to believe, right? Is it? Yeah. So anytime you see some operator corresponding to crossing a wall in situation where you have a curve count, you could expect, well, maybe this really comes from variation of some stability condition. And this much we don't know. And that's this. But you can imagine.
I answer it.
Yeah.
I'm
Yeah.
stupid.
But you.
Suppose
Uh-huh.
you have some category.
Mm-hmm.
Then when you crossing the wall, you have a function.
Right.
When you go around,
Mm-hmm.
you have identity on the level of K field,
Okay.
but actually you don't expect that the functors.
No, even in this Rome situation, you come around. I mean,
What
you
I
get yourself.
expect, you have some two categories,
Uh-huh.
and here you have identity, the map of two functions
Uh-huh.
with identity.
Right.
I expect to have additional.
This relates to the K pi 1's question. Are these questions are K pi 1? Are the spaces are K pi 1? Yeah, this I don't know if they're K pi 1 or not, but you can imagine something like this. Yeah. Right. And so so in other words, this is opposed to Roma's situation. I mean, I don't know. Roma's an ice situation or something. There's some theory that Roma actually proved about the monodromy of these guys, which I'll get to that. But as opposed to that, there we have a multitude of matrices. And here we have one elliptic matrix. So there's just one object that encodes them all.
So
do you say that this has to do with the fact that pi 2 of this space vanishes?
No, it just has to do with the fact that there's. No, I mean, okay. Well, let's. No, I don't want to say that. What I want to say that this, I'd like to say that this is to relate it to the thing I want to discuss next. This, well, is that this is really this category, whatever that is. These are supposed to be this boundary condition in the three-dimensional, in 3D theories corresponding to X. And this is just there's just like a flow interface for. I mean, you choose some parameters in the theory, you can implement it by an interface that really does that stuff for you. So this is what you certainly expect there. Right. So maybe now to summarize. So to summarize is that we would like to see. So I guess I defined a notion, very simple notion of dynamical groupoid. It's a collection of it's a hyperplane arrangement, and a collection of operators for every wall that satisfy the braid relation. And I additionally assume this kind of quasi-periodicity of these operators, which is satisfied in this situation we want. And now I said the two main examples of this come geometrically, and they come in the situation when my torus is either the Picard torus of some variety, or it's the maximal torus in automorphism group of a certain variety. And then, in this case, these commuting difference operators come from either the quantum difference equation or the shift operators. And of course, well, I mean, the symplectic duality is not the topic of this particular set of lectures, but it certainly permutes these two sets. And then maybe to be more somehow to reiterate what I said is that the very first notion. So it's like maybe another thing. So this is when you take the Lie theory, subtract the groups. Maybe even before Cartan-Lustig theory, what you would like to preserve is the notion of roots. And so the roots are these finitely many vectors, such that my arrangement is given by pairing. By the equation, this pairing is an integer. And you can ask, what are the roots? So the roots are the roots in the equivalent situation are just very, very simple. They're straight generalization of Lie theoretic situation, namely just the weights, how you define the roots, the weights of the torus in certain linear representation. And roots in the scalar situation, well, I guess Davesh started this discussion, and it's slightly, so there's a certain depth to that. Namely, if we go back here, I said that this is, so there is this affine arrangement, and there's corresponding central arrangement. This corresponding central arrangement is easy. That is just the central arrangement corresponds to decomposition of your H2 into the ample cones of various birational models. But that determines the vectors only up to proportionality. Right? And the main example, for example, this is if I take, so the main example is when maybe I'll write the main example here, which is really main, is that if my X is the Hilbert, is the Hilbert scheme of points, in which case peak is one-dimensional, so there's only one thing you can do. This is positive cone and negative cone. So this is my central arrangement. Whereas the arrangement I want are all the fractions with denominator at most n. So this means AB with b's at most n. And so that says that the roots, in other words, the roots, the scalar roots here are just to say, well, the positive scalar roots are 1, 2, up to n.
Except 20.
What?
B is more than 1.
You can assume the situation that for some of these walls, the operator is trivial, and this is just really just for helpless scheme. It's just really an accident that just happens to be. For high rank shift, it's really so. So there's some interesting in terms of geometry. There's some interesting. So the precision of the ample cones determines this root vectors up to proportionality, and how many of them you take. There's certain geometry in that, which I'm not going to discuss now. But this is it already appeared both in the actual formulas both appeared both in Davesh's and in Van Stock. I mean, for Nakajima variety, the answer is you take roots of a certain Lie algebra, and then the root is a vector, and there's an ordering on this root. I mean, there's an ordering on this root, and so you'd like the roots that are less than your dimension vector. Less or equal than your dimension vector, which is your dimension vector is n, and so you take the roots are integers, and you take all the integers up to n. So all right, so this brings us to the beginning of discussion of actual geometry. Pashi, did you want to ask something? Or?
Yeah. So this thing when you said you have sheets on the
Mm-hmm.
space of X and the map to sheets in the space of X. These are equivariant sheets.
Yeah, they're all invariant with respect to everything. Yeah, right. Most importantly, where is Q? I kept writing the variable Q. Q is not the variable in the quantum group. Q is just free parameter. Geometrically, it's the group that acts. So you have loops. Loops are the maps from somewhere, and Q just rotates that somewhere.
But in particular, this elliptic R matrix depends on spectral parameter.
Yes.
Elliptic function of the spectral parameter.
Yes.
And it has poles with respect to this parameter.
Yes, these are the roots.
No, but what I mean is that these poles are analogous to the fact that in the usual monodromy case, it depends on the class. So what are these poles?
But the poles poles in the monodromy are precisely the poles in your equation.
But this functor, functor between categories of sheets. So how do you see?
Well, because there's some, because you have some. You have to discuss what sort of sheaves you allow. I mean, this has a certain. There's some improperness there. You have to.
Yeah, probably the sheaves are kind of infinite in some sense, and when you pass to k0 somehow, you actually have to somehow make things serious.
No, but I mean, you have to discuss what I mean. How if you have like a theta function in denominator, what is the character of? You have some kind of discussion what that's supposed to be.
But then I mentioned an example when somehow you have X and a flope, and you can show that some kind of categories of sheaves on L. X.
Yeah, I mean, I have plenty of examples where I can show lots of things. So let's just wait. So
But you didn't answer the question.
yeah. All right. So to start with this, so maybe so what we're gonna this is I'm actually going to start with what Sasha already discussed last night, and that the notion of where is that supposed to come. So looking from a certain distance, enumerative geometry and physics are essentially identical. I mean, enumerative geometry is just a way to make to really make sense of a certain physical computation, right? I think this is about in 10 or so minutes. So maybe I'll explain. So this is enumerative geometry. This will be enumerative geometry / physical origin of this construction. And so, what? Right. When the general discussion that Sasha started has to do with three-dimensional theory. So this is there's some space-time manifold which is M3, but really I don't know how to make sense of anything unless this is a product of a curve cross S1. So let's just stick to that direction. And so then we will. Your space-time is a product. Then you can take like a Hamiltonian approach in that you write some vector space associated to just that surface, and you take the traces of various operators over that space, give you the quantities you want to compute. Is that clear? Now, what is this theory is going to look like? Well, I don't know if you're going to like it or not, but I'm going to just some general physical principles are extremely useful in life, and even though they're physical, they're not rigorous, but they're very useful. And so, what does any physical theory looks like if you look from far away? If you look from really, really far away, for example, you think of a gas filling an infinite volume, then there'll have to be system in an infinite volume will have to be in some one of its ground states or vacuum. So for a gas, that means there's for given density and given temperature, there's unique. I mean, the equation of state of the gas tells you that all the vacua are just parameterized by two quantities. The moduli space of vacua is two-dimensional, real two-dimensional. And so then if you somehow look a little closer, if you allow certain perturbation over that vacuum, well, what is going to look like? That's going to look like a modulated vacuum. Like it's like for a gas, that means that the density and the temperature will vary slightly from point to point, obeying a certain equation. So from this perspective, any physical theory looks like a sigma model, that is to say a map, from your space, which is in Hamiltonian approach will be just that surface, to the modular vacuum. And if the theory is to be supersymmetric, then you'd like this sigma model to be similarly supersymmetric. That is to say, your space of vacua should you should be able to write this kind of sigma model with enough supercharges, which in the situation that we're discussing here means that so we're studying, in other words, so zeroth approximation, we study maps from a Riemann surface, which is our space, to the modular vacua, and to have enough supersymmetry, what we would like to do, well, to have the right amount of supersymmetry, what we would like to do is we would like the target to be roughly holomorphic symplectic, and the map to be holomorphic. So our theory is roughly holomorphic maps from curves to some variety x, which is roughly holomorphic symplectic.
Now what you want to get will depend on the conformal structure.
Yes, right. That's right. Yeah, this is a holomorphic. And when we insert some operators, means like we measure, for example, we measure the temperature at various points in fixed time and so forth. Right? So it means there's some points here that curve contains. Some operators would like to insert there. And then, I remind you, this is all in Hamiltonian approach. Means we're supposed to write some vector space and take the trace of some operator. Means to a data, like what we really like is we would really like, well, ideally maybe we like a complex on the moduli spaces of pointed curves, but at least an element. So from this data, what we would like is an element in K theory or dB Koch if you want, but on MGN bar. That makes sense? With the rank, generic rank, being something like the K, so there's going to be a sheaf, roughly a sheaf on this with rank, sorry, no. So this is, no, I said it incorrectly.
What happened to X?
So integrating over maps to X from a fixed curve, you're going to give you an element here. This adjoint formal power series in Z. Sorry.
Where Z is what?
Z is counts the degrees. This map has a certain degree. You weight your map by Z to the degree. You sum them up. So for fixed degree, it's a proper thing. You integrate something over that, you get an element in here. That makes sense? And so what are the what is the
What is your map is a kind of chunky? What is the map? You can see the spatial maps of a curve to fix one.
uh-huh.
Now, are you taking then you map it in K theory? Because I think the energy of
So you have a right. So maybe I'll define. You have a. Maybe I'll say a little bit more specific in what sort of maps are we going to actually mathematically handle. But then when we have some moduli space, it's like in Daveshi's-Stock. We have some moduli or in Jake's for that matter. There's some moduli spaces of maps here. You pull back. It has some like a virtual structure sheaf. Not exactly virtual. Some symmetrized, better object, symmetrized virtual structure sheaf. You'll pull back K theory classes from X using your revelation map, and then you can push it forward, and so you get the element of K theory of that object. It means for every you can put insertions, or maybe you should say separate. So this should be a map from so many copies of K theory of X to here. So maybe I'll write like this: K theory, and K theory of X. So many copies here, and then this is well still T equivalent, but T doesn't have. Or maybe there's a right, and so maybe it's actually it's a good point to stop, but yeah, maybe it is a good point to stop actually. So this is so this.